Somewhere in Dubai, there's a company with 2 employees. Dubai. No team of 100 engineers, no research department, not a dozen specialists in fluid mechanics, thermodynamics, and manufacturing processes. 2 people and software that accomplishes in a few weeks what engineers have called impossible for decades. In December 2025, this company built 2 rocket engines. Not just designed, but built, tested, and even fired, including an Aerospike engine. One of the most complex and at the same time most sought after engine architectures in the history of spaceflight. Engines that are so difficult to manufacture that in 30 years, barely a handful of teams worldwide have managed to get them running, let alone put them into operational use. From specification to first ignition in less than 3 weeks. The company, it's called LEAP71, and what they're doing is quietly changing the fundamentals of engineering. My name is Sirwan, and this is Mars Chronican. Before we dive into the technology, we need to understand the 2 people behind this story. Josephine Lissner is an aerospace engineer. She studied at the University of Stuttgart and then helped design the aerodynamics of Lewis Hamilton's championship car at the Mercedes-AMG Petronas Formula One team. And then she worked at Porsche Motorsport in their newly founded Formula E team. She is also an ultramarathon runner. In 2018, she won the 110-kilometer Hadrian's Wall ultramarathon. This is relevant because it reveals something about her way of thinking. Lissner is someone who solves problems through consistent step-by-step work. This shows her uncompromising ambition and perseverance. Besides, it didn't just happen by chance that you ended up working at the top of motorsports. The second person is Lynn Kaiser. He is a serial entrepreneur and has been developing software since his childhood. Before he co-founded LEAP71, he led Hypergenic, a company that also specialized in algorithmic design. There he laid the technological foundation on which LEAP71 is built today. The 2 met at Hypergenic. In 2023, they founded LEAP71 together in Dubai. And then they did something that has never happened before in the history of engineering. To understand what LEAP71 does, you first have to understand what engineering has been up to now. An engineer designing a rocket engine spends months, if not years, doing it. He starts with basic physics. Thermodynamics, fluid mechanics, combustion theory. He develops concepts, calculates parameters, selects materials. Every curve, every channel, every drilled hole is drawn manually in CAD software. It takes forever because everything has to be done by hand. Then come simulations, feedback loops, corrections. Then it's manufactured, then tested and analyzed. They then iterate based on the analysis data. That means the design is revised and the whole loop starts from the beginning. This is done until the test data is satisfactory, meaning it meets the requirements. A modern rocket engine is the result of years of collective human expertise. As a rule, it contains the knowledge of hundreds of engineers over decades. And that's exactly the problem, says Kaiser. Engineering, he argues, is incredibly slow because it was never truly computerized. Computers were used in engineering as a drawing tool, as a simulation tool. But the actual thought process, the actual design logic, always remained with humans. LEAP71 wants to change that. They don't call their approach AI, nor do they call it a generative system, even though it closely resembles one. They refer to their approach as computational engineering, meaning computer-aided engineering. A little bit of marketing is necessary too. That's perfectly fine. The heart of LEAP71 is a piece of software called Neuron. Similar to the word neuron, as in a nerve cell, just spelled differently. Neuron is not a CAD program, AI assistant, and not an algorithm in the classical sense. Neuron is, and this is the precise description, a large computational engineering model. A system that has translated the entire logic of engineering into code. That means physics, manufacturing rules, material properties, and practical experience from real-world tests. All of that is coded into a deterministic system based on fundamental physical principles. You give Neuron a specification. For example, I need an engine with 20 kN of thrust, powered by liquid methane and liquid oxygen, suitable for orbital applications. Neuron generates the design as production-ready geometry, immediately ready for additive manufacturing. So, for 3D printing here, you don't just get rough sketches or ideas, but truly finished designs. That's the difference compared to everything that has existed so far. Neuron doesn't generate images or texts, it generates physical objects that have to work in the real world. And physics doesn't allow any mistakes. Listener describes it like this. When an engineer meticulously translates his knowledge and methods into computer code, he becomes orders of magnitude faster. That doesn't replace the engineer, but multiplies productivity. That is the philosophical core of LEAP71. Engineering encoded in a system that executes it at the speed of computers. Now we come to the results, because theory is one thing, fire is another. Big claims are made every day. The question is whether they can actually be put into practice. In June 2024, less than a year after its founding, LEAP71 tested an engine generated by Neuron for the first time, with 5 kilonewtons of thrust. Completely designed by the software, completely printed in copper using additive manufacturing, no manual intervention in the geometry. And lo and behold, it worked on the first try. That's an almost unheard of occurrence in engine construction. Engines rarely work on the first test. It's normal to test, analyze, correct, rebuild, and test again. This cycle typically takes months. LEAP71 simply skipped it. The comparison might be a bit off now, but it's kind of like meeting for a first date and 3 weeks later you're holding a baby in your hands. After that, more tests followed. Engines with different thrust classes from 1.5 to 7.5 kilonewtons, with different materials and different configurations. Always the same pattern, specification in, design out, print, test, and it kept working every time. That's really impressive. Because there are certainly occasional lucky hits, but delivering repeatable results is a whole different thing. And then, in December 2024, something happened that made the spaceflight community sit up and take notice. The Aerospike engine. To understand why this is so significant, we first need to briefly explain what an Aerospike actually is, and why, for decades, it has been considered the most difficult engine architecture in history to master. Conventional rocket engines have a bell shape. This bell is designed to work optimally at a specific atmospheric pressure, either at sea level or in a vacuum. The problem? An engine that works optimally at sea level is inefficient in a vacuum, and vice versa. An Aerospike solves this problem with a radically different design. Instead of a bell, it has a central spike. A spike with a ring-shaped combustion chamber around it. The exhaust gases flow outward and automatically adapt to the ambient pressure. That makes the Aerospike more efficient than any bell nozzle from sea level all the way to vacuum. That sounds perfect, so why doesn't everyone build an Aerospike engine like that? Because they're brutally difficult to manufacture. The internal geometry is so complex that conventional manufacturing methods can hardly produce them. Cooling the spike is a thermodynamic nightmare. And controlling the flow behavior of the exhaust gases in this inverse, that is upside-down architecture, requires an understanding of physics that is at the very limit of what is possible even for experienced engineers. As I said, in 30 years, only a handful of teams worldwide have successfully tested an Aerospike engine. LEAP71 did it in just a few weeks. The fully 3D printed copper engine with 5 kilonewtons of thrust worked on the very first test. And that was just the beginning. Short pause, because this moment deserves it. If what you just heard fascinates you even half as much as it fascinates me, then hit the hype button now. Not out of politeness, but because that's exactly what the algorithm needs to show this video to people who don't know stories like this yet. A subscription costs you nothing and keeps you up to date when LEAP71 reaches her next milestone. By the way, our channel members also get to see such videos days or even weeks in advance. The link for that is below. Let's continue. It's about to get even more absurd. In December 2025, they raised the bar dramatically once again. This time, not just one engine, but two in a single test campaign. Both engines generated 20 kilonewtons of thrust. That's about 2 tons of thrust. Both burned with liquid methane and liquid oxygen, the so-called methalox fuel. The same fuel that SpaceX uses in the Raptor engine of Starship and Blue Origin uses in its BE-4 engine on New Glenn. The same fuel that is considered the future of rocket engines. Clean, powerful, and producible on Mars. The first of the two engines was a conventional bell nozzle. The second was a full Aerospike. Two fundamentally different engine architectures. Both generated by Neuron. Both in less than 3 weeks from specification to first ignition. That's completely absurd in the best sense, of course. For comparison, a typical commercial rocket engine development program takes 3 to 5 years, sometimes longer in the best case. The Raptor engine from SpaceX has been in development for over a decade now, but what LEAP71 produced in March 2026 surpasses even that. In collaboration with HBD, a Chinese manufacturer of large-scale metal printing systems, LEAP71 has produced the largest 3D printed Aerospike ever made. The engine is designated XRA-2E5. The naming may still leave something to be desired, but that's not the main point here. The engine is 1 meter tall, produces 200 kilonewtons of thrust, which is about 20 tons, and also burns with methalox. It was completely printed from Inconel 718, a high-temperature resistant nickel alloy that is the standard for 3D printed rocket engines. The printing took 289 hours, so a little more than 12 days. Continuously with a 10 laser system, one of the most powerful metal printing systems in the world. Please take a moment to realize what we're talking about here. If you had said things like this a few years ago, you would have been committed on the spot. The result is a monolithic object. A single component that contains everything that used to be made up of hundreds of individual parts that were milled, welded, riveted, screwed, sealed, and assembled. No seals, no screws, no connection points where pressure or temperature could endanger the system. Here, the philosophy, the best part is no part, is taken to the extreme. So parts that don't exist can't fail either. Listener describes Aerospikes as the holy grail of space propulsion and at the same time explains why they are so difficult to manufacture. The complex geometry has historically made them extremely difficult to design and manufacture. And the combination of computational engineering and large-scale additive manufacturing makes it possible to actually produce this grail. We've mentioned it briefly, but now we need to explore the technology in more detail. Because there's a question that inevitably arises with all of this. What exactly is Neuron? And even more importantly, what is it not? That's important because the term AI is used so excessively in public discussions that it's almost lost its meaning. ChatGPT is AI. Image generators are AI. Recommendation algorithms are AI. And now rocket engines too? The answer? Neuron is AI, but a completely different kind of AI. Generative AI systems like large language models work probabilistically, meaning they operate with probabilities. They have no real understanding of the world. They have learned patterns from enormous amounts of data and can convincingly reproduce these patterns. That is powerful, but it is also prone to errors. A language model can give wrong answers with great confidence because it doesn't know the truth. It only knows what sounds probable. That works for text and now also quite well for images. And even for videos now. But certainly not for rocket engines. Or maybe a rocket engine that collapses at 1,500 degrees Celsius and a chamber pressure of 300 bar can have fatal consequences. Physics does not allow probabilistic approximations. Neuron is therefore deterministic. It is not based on statistical patterns from training data. It is based on encoded physics, thermodynamics, fluid mechanics, material science, and manufacturing conditions. All of this was translated by Lissner and Kaiser into explicit, verifiable logic in code. That means Neuron doesn't make predictions. It calculates. Calculations are traceable, verifiable, and reproducible. Exactly what you need when working with fire and high-pressure gases. There is a second technological pillar without which LEAP71 wouldn't work. Additive manufacturing, 3D printing in metal. Conventional manufacturing is subtractive. You start with a metal block and mill, turn and drill until the desired shape remains. That works excellently for simple and moderately complex geometries. But beyond a certain level of complexity, it becomes impractical. Internal channels that snake through a component, cooling structures that run through the material like veins, geometries that need to be accessible from the inside. All of that is either impossible or insanely expensive with subtractive manufacturing. Additive manufacturing turns the principle around. You start with nothing and build up layer by layer. The complexity of the component doesn't cost anything extra. A simple sphere is just as labor-intensive to print as a highly intricate integrated cooling system. Put the file into the software, slice it, and you're good to go. That's a simplified explanation, but crucial for Neuron. Because Neuron isn't limited by the logic of conventional manufacturing data or techniques, it can generate geometries that no human would ever have drawn manually. Not because no one could, but because the manufacturability of such shapes simply wasn't possible before. The result is engines that look like living structures, cooling channels that wind organically through the material, injector heads whose density and complexity are reminiscent of coral reefs, structures that are optimized to deliver the greatest possible performance with the least possible material. Even though it looks beautiful, this isn't about aesthetics, it's about physics. Speaking of 3D printing, here in the studio, we currently have the Raptor engine from SpaceX and the iconic F1 engine from the Saturn V, not made of Inconel, but of PLA. But it's still impressive that someone like me can just make this at home. Printed with the Core One from Prusa, our sponsor, and the printer we also use to produce our licensed Starship and SLS models. If you want to start 3D printing yourself, the QR code is on the screen right now. The link is down in the description. And now back to the things that are made of Inconel. Let's move on to scaling. Because so far we've been talking about engines up to 20 kN. That's impressive, but these are engines for smaller satellites, kick stages, and upper stages. So, what about real rocket engines? In November 2025, LEAP71, together with Nikon SLM Solutions, a German pioneer in metal printing, produced the injector head of an engine in the XRB2E6 class. 600 mm in diameter, one of the largest and most complex 3D printed aerospace components ever produced. The XRB2E6 is a Methalox engine with 2000 kN of thrust. So 2 meganewtons or about 200 tons. For comparison, the Raptor 3 engine from SpaceX, the most powerful production engine in the world, produces about 300 tons of thrust, and Blue Origin's BE4 about 280 tons. LEAP71 is therefore in the same performance class. And even more radical, the engine is designed as a full flow staged combustion engine, FFSC. So, full flow staged combustion. That's the same cycle used by the Raptor engine, the most efficient, complex, and difficult cycle of chemical rocket propulsion. For decades, it was considered too difficult for most players in the industry. What's special and at the same time challenging is that with the FFSC, both engine components are completely routed through their own preburners before they enter the main combustion chamber. Each component drives its own turbopump in the process. That maximizes efficiency, but it also means that hot oxygen-rich gas flows through one side and hot fuel-rich gas flows through the other, both under enormous pressure and extreme temperatures. The system has to control that instability while keeping all flow and burn rates balanced. That's exactly what made it virtually impossible for decades. Don't worry, it only sounds so complicated because it actually is. SpaceX took years to master this cycle. LEAP71 generates the injector head for this completely autonomously, without any human intervention in the geometry. What does that mean strategically? The classic bottleneck in rocket development was never the physics. We've known the equations for decades. The bottleneck was time and expertise. An experienced propulsion engineer is rare. In addition, he needs years of training, years of experience, and even then, his capacity is limited. We humans only have a limited number of productive hours per day. Neuron has removed this limitation. When Listener has coded the logic of an engine concept into Neuron, this system can generate thousands of variants in the same amount of time it would take a human engineer to draw a sketch. Each variant is physically valid and ready for manufacturing. That changes the game for everyone who wants access to space propulsion. Not just for major powers with huge defense budgets, but also for small companies, emerging countries, and players who couldn't afford their own engine development until now. This is exactly what LEAP71's partnership strategy shows. In June 2025, LEAP71 entered into a strategic partnership with Aspire Space, a Luxembourg-based space company that has since moved all its primary operations to the United Arab Emirates. Aspire wants to develop a fully reusable launch vehicle system that can deliver up to 15 tons to low Earth orbit. The entire propulsion system comes from LEAP71, with the kind support of Neuron. In March 2026, the Exploration Company, a European space company with over 400 employees known for the Nix resupply capsule and the Typhoon engine, signed a 5-year license agreement for Neuron RP. The Exploration Company will integrate the software into its own engine development. That's a significant signal. They're not a startup in some garage. This is a serious European space company that actively works with ESA and private customers. And they trust LEAP71 with part of their core technology. In addition, LEAP71 has presented a concept for a hypersonic pre-cooling system in cooperation with Farsoon Technologies. 1.5 meters tall with a single purpose: to cool air at hypersonic speeds enough for an air-breathing engine to work. The key building block for single-stage spacecraft that take off like an airplane and fly directly into orbit. Single stage to orbit, SSTO. A dream of spaceflight for decades. Technically out of reach for decades. The pre-cooler is still just a concept, but the concept exists. Printed, measurable, tangible, and at their speed, it's a matter of weeks before we see hardware and initial tests. I'd like to pause for a moment here, because LEAP71 is a small company that produces extraordinary things. But it's important to be honest about where we are in this process. The engines have been tested, but not all of them are certified for orbital use. Validating an engine for space use, especially for manned missions, is a long, rigid process. Hundreds of tests, qualification runs, and safety verifications. And that's a good thing. LEAP71 is still in the basic validation phase. They are proving that their methodology works. Neuron can generate engines that ignite on the first try. That's remarkable, but it's not the same as a qualified propulsion system for an orbital mission. The road from here to there is still long, and it will show whether the methodology holds up under the pressure of a full qualification program. But the starting point is so strong that the question is no longer if, but when. So next, the 20 kilonewton that LEAP71 tested in December 2025 corresponds, according to their own statements, to about 10% of the thrust class they want to test in 2026. That means by the end of this year, LEAP71 is planning a hot fire test in the 200 kN class. 20 tons of thrust, and the manufacturing validation, which is the foundation for the meganewton engine, is already underway. World's largest metal printing systems. If LEAP71 sticks to these schedules, the company will have validated engines in a performance class that enables real orbital missions by the end of 2026. 2 people, 3 years from zero to rocket engines in the meganewton range. There is no equivalent to that in the history of engineering. But the real significance of LEAP71 doesn't lie in the engines. The engines are the demonstration. The real innovation is the insight behind it. Engineering has been a linear process until now. Idea, calculation, design, manufacturing, testing, iteration. Each step took months. Every mistake cost time and money, and that limited what was possible. Not the physics, not the material, not the money, but the time. Neuron radically reduces this time by orders of magnitude. And once this methodology is applied to fields like heat exchangers, drive systems for electric mobility, biomedical implants, construction components for satellites or architecture, then we're talking about the question of how humanity will build things in 20 years. Listener put it this way in an interview: engineering knowledge, which until now was stored in the minds of experts and lost when they retired, can now be encoded into systems that preserve it forever and make it accessible to everyone. It's nothing less than the democratization of engineering. 2 people, 1 office in Dubai. Software that designs in seconds what takes people months, and engines that fire on the first try. LEAP71 is the most important unknown company in spaceflight. Not yet. My name is Sirwan, and that was Mars Chronican. Thank you for tuning in. Per aspera, ad astra. Our engines? Police? The greatest possible performance. So, now the engines want to go. Per aspera, ad astra. Wait, let's try a different pronunciation. Per aspera, ad astra. Again. That's unusual.